After having spent time learning about the general power rule for integration and learning the substitution technique, this lesson should seem fairly straightforward because all that we want to do is add the exponential integral to what we've already been doing, and that should be very simple because the derivative rule for exponential functions is so simple. In fact, we know that the derivative of e to the x is e to the x, so it shouldn't be any surprise at all that the exponential rule for integration simply says that the integral of e to a power u du is equal to e to the u plus c. So today's lesson is basically combining this new one piece of information with all our techniques of substitution that we learned earlier. Let's just jump right into it. Suppose I give you the integral e to the power of 7x plus 5 and ask you to integrate that. The integrand is e to the 7x plus 5. If you look back at the rule for integration for exponentials, you can see that the 7x plus 5 plays the role of u. And in our substitution technique, we know we have to calculate du over dx and then turn it into just du. I think at the point where we can just skip that middle step and say that if u is equal to 7x plus 5, then du is 7 dx. So when you look back at the form, you can see that the differential part, the du, needs a 7, not just a dx. But that's okay, because we learned with substitution that we can insert a constant, a numerical value, if we need to, as long as we multiply on the outside by its reciprocal. In other words, we're compensating because 1/7 times 7 is just 1, and we really haven't changed the value of the integral at all. That's our basic substitution technique, and that doesn't change just because we're changing rules. At this point, you can see the substitution. The 7x plus 5 was originally set up as u, and we just calculated the differential du to be 7 dx. We see a 7 dx there, so we can replace the 7 dx with du and the 7x plus 5 with a u, and now we have 1/7 times the integral of e to the u du, and that fits our exponential rule for integration formula, which says the answer is just e to the u. Don't forget about the 1/7, but the answer to the integral part is e to the u. Now, the original problem didn't have any u's in it. We put that in as a substitution technique. So in the end, we want to get rid of the u and put back in the 7x plus 5. And that's honestly all there is to this. It's the same substitution technique as before, applied to the exponential rule, but otherwise the same. Let's tackle another one. Suppose I have 7x times e to the 9x squared, and I want to integrate that. Well, again, I'm looking at the exponential rule, and I can see that the exponent on e will be our u, so it's pretty clear that the u is going to be 9x squared, but be careful. I'm pretty sure, and thinking ahead, when u is equal to 9x squared, du is going to be an 18x dx. I have the x dx sitting there, you can see, but the x is on the left side of the exponential. I think I'll slide it over, and also remember that the numerical value can be pulled outside of the integral sign just so it's out of the way. So as you learn this process and get better with substitution, what you're going to see is that these integrands can be tidied up or made to look like you need them to look within limits. You can pull a factor out, a constant factor outside the integral sign. Within the integrand, you can rearrange the factors any way you like, and since I can see ahead, I'm sort of getting ahead of myself in a way, but once you do this enough, you can kind of see that. I can see that when I let u be 9x squared, the differential is going to be 18x dx, so I can see that the x needs to be over next to the dx, and as long as I keep it inside the integrand, I can move it around in any order I want to. But I'm still missing an 18. So I'm sort of leaving room here. I know I need to put an 18 in there by the dx, by the x dx. I can do that as long as I put a 1/18 on the outside, which will eventually get multiplied by that 7. The more you practice this, the better you get at it. Anytime you try something new that has several components and you have to think about things, it's an adjustment period, there's a practice period, there's a learning curve. You have to be willing to spend the time, go back, try it again, think about what you did until it becomes second nature. So you can see what I've done with this. I've sort of massaged it. That 7 needed to be pulled out, so I pulled it out of the integral. The x needed to be put over next to the dx because I could see that it was going to be part of the differential du. The more you practice this, the better you'll get at it. Then you notice that it's missing an 18. That's okay because it's just a constant. I can put an 18 in as long as I multiply by 1/18 on the outside. Those are the sorts of skills that you need to practice over and over and over again until they become second nature. So now I can do the substitution. The 9x squared is the u. The 18x dx is the du. So I can completely bring out all the x's now and just write it in terms of u. And remember, that 7 times 1/18 is 7/18. And now the only thing left to do is get the x's back into the problem. So you remove the u and put back in 9x squared. Oh, you actually integrate as well. I almost forgot the main part. You integrate e to the u and get e to the u. The 9/18 is still there. And I haven't been emphasizing it, but don't ever forget the plus c. And then you want to substitute and put the x's back in. Again, the more you practice, the more you go through this over and over again, the more it's going to just become a rote process, and you don't have to struggle so much step to step. And you can concentrate on more on not making careless mistakes rather than focusing on, well, what do I do next? What do I do next? The more you do this, the more that part of it will be natural, and you can focus your attention more on being careful and cutting out careless mistakes. So the answer is 7/18 e to the 9x squared plus c. Let's do another. Suppose I've got this. Well, if you've played the game now as much as we have already, you can probably see ahead enough to know that 2x plus 6 somehow in some form is going to be part of the differential. So it's going to shift over next to the dx in some form or fashion. And if you think about it, you can see that the exponent of the e has got to be the u. So that's going to be x squared plus 6x. That's pretty clear. The differential is 2x plus 6 dx. Aha! See, I knew that had to happen. So that 2x plus 6 being part of the differential needs to be slid over. Again, it can't come outside the integral sign because it involves x. But as long as it's inside the integration sign, inside that integration, then you can move those factors in any order you want to. And I know I need that 2x plus 6 over next to the dx. Well, at this point, the game's practically over. I can see that the 2x plus 6 times dx is right there, so I can call that du. I already know that x squared plus 6x is u, so when I substitute, all I've got is the integral of e to the u du, which, according to the formula, is just e to the u plus c. And of course, the last step, as always, is to take the u out and put back in the x value. So I end up with e to the x squared plus 6x plus a constant of integration c. I might also mention that you can always take the derivative of your answer and make sure you get back what you started with. That's another way to check to make sure you didn't make a careless mistake. The more you practice this, the easier it becomes. Let's take a problem very similar to this, though, and solve it. Notice this is very similar, but instead of having 2x plus 6 as the multiple, I've got x plus 3. That's got to change things because I know that u is still going to be x squared plus 6x, which means that du is still going to be 2x plus 6 times dx. But this time I don't have a 2x plus 6. I just have an x plus 3. There's got to be something that's going to get me out of that jam. And if you think about it a minute, you can easily see what it is. There's a 2 here, and there's a 2 inside that 6. So I can factor a 2 out of that 2x plus 6 and get 2 times the quantity x plus 3 dx. Now I can see how it's going to work. Now I've got that x plus 3 as part of the differential here, and I've also got it inside the integrand. So now I know what to do. I'm going to go up here, I'm going to move the x plus 3 over next to the differential dx. But then I notice that I need a 2. So I can handle that as long as it's a constant. So I can put a 2 in beside the x plus 3 dx as long as I put a 1/2 on the outside. That allows me to do my substitution. The 2 times the quantity x plus 3 dx becomes the du. The x squared plus 6x becomes the u, and I end up with 1/2 times the integral of e to the u du. The integral of e to the u du by formula is e to the u plus c, and that 1/2 just sits there. Final step, as always, is to get rid of the u and put back in the x value, which in this case is x squared plus 6x. So there you go. And you can see how these things flow through the same sort of way each time. You do have to practice. Just watching me do it or stumbling through it once or twice without ever quite understanding every step, that's not the way to learn how to do this. You just keep doing it over and over again, practicing until it becomes second nature. Now, let's switch to the rule for integrating certain things that actually come out to be logarithms. And it's based on the derivative rule for logarithms. The derivative of the natural log of x is 1 over x. So if you're going backwards and doing antiderivatives or integrals, shouldn't the answer to be, well, the integral of 1 over x dx should just be the natural log of x plus a constant of integration? And that's almost right. There's just one other factor going on here that you have to account for, and that is the domain of the natural logarithmic function is the positive real numbers. You can't take the log of 0 or negatives. So you have to adjust for that in that formula so that you can never take the log of a negative or 0. So because of that domain restriction for the natural logarithm function, you have to adjust this formula slightly and put an absolute value around whatever you're taking the log of. That way, no matter what you plug in for u, you don't get you're never taking the log of a negative number. Other than that, this log rule for integration is just what we thought it would be. You just have to remember that because of the restricted domain of the natural log function, you have to account for the fact that you could never let a negative number pop in front of a natural log. But anyway, that's our log rule for integration. Let's just work some problems. Actually, I do want to say one more thing. If you remember back to the general power rule for integration, I didn't really emphasize it much at that point because I intended to come back to it here. But we always said that n cannot be minus 1 for that formula. Now you're going to see why if you haven't already. If you take minus 1 and plug it in for n in that formula, you'll get the integral of u to the minus 1. But u to the minus 1 is just 1 over u. Well, look, that's where the log rule comes in. So the log rule for integration basically fills the gap in the general power rule for integration. It had a gap where you couldn't let n be minus 1. And you can see why now, because the minus 1 case is actually the log rule. So sort of nice to know. But let's take this and run with it. Let's just work some problems with this formula. You're still going to go back and deal with all the problems of doing substitutions and things like that, but the process is the same. Start off with, say, the integral of 1 over the quantity 7x plus 1. Start off the same. You can see that the u is going to be the denominator, so it's going to be 7x plus 1. Du will be 7 dx. You can see, though, that there's no 7 with the dx, but that's okay. You can put the 7 in as long as you multiply by 1/7 on the outside. Now your same strategy that you were doing with the exponentials and even before that, you substitute for u. 7x plus 1 is u, 7 dx is du, so that integral becomes 1/7 times the integral of 1 over u du, and the formula for the log rule says that comes out to be the natural log of the absolute value of u plus c, and remember that 1/7 is sitting there, and don't forget to put the plus c, And as always, the final step is to get rid of the u and put back in what u is equal to, which in this case is 7x plus 1. Simple. How about this one? It looks a mess, but it's something over something, and just as a little hint, anytime you see in a fraction like that with the power down bottom being 1 more than the power up top, that's sort of a clue to let the denominator be u. And once you see that, you've got to hope that somehow this is going to turn into a 1 over u type problem. Well, think this through. If this is really going to turn into a 1 over u type problem, you need to get a 1 in the numerator. Well, you can do that as long as you bring the numerator out front and put it with the dx, because remember, that's like over 1. So you're really not changing anything by putting it out there. And what you gain is it begins to look like what you want. You're trying to get it to look like that. Well, let's go for it. We're saying that the denominator has to be u if it's going to fit into that formula. Well, let's compute the differential. The differential then will be 3x squared plus 6x plus 12 dx. Well, that's not quite right. We don't quite have that, but I do notice that there's a common factor of 3. Maybe that gives me some hope. If you factor that 3 out, bingo, you see it now. You've got an x squared plus 2x plus 4 there and there. That gives us hope, and we've got a dx there and there. So the only thing we're missing is that 3, but that's okay. As long as we put the 3 on the inside and the 1/3 on the outside, we can create the differential that we need so that we can do the correct substitution. So as you can see now, u is the denominator of that fraction, so you get you'll get 1 over u, and then the whole complicated expression involving x's and dx's becomes du. So when you substitute, that whole nasty looking problem comes down to the form of 1/3 times the integral of 1 over u du. Well, that fits the formula exactly. So that answer will be 1/3 times the natural log of the absolute value of u plus c. And as always, the last step is to take the u out and put back in what it was equal to. So even though that problem looked a little nasty, once you see the pattern, the process becomes the same. You have to fit it into one of the formulas that you're working with. In this case, the one that generates the natural log of the absolute value of u as the answer. Well, how about this one? Again, it looks worse than it is. I'm seeing this formula right here, and it's just almost begging me to let u be the denominator, so I'm going to try that. So if u is equal to 4 plus e to the x, the differential, the derivative of 4 is 0, and the derivative of e to the x is e to the x, so the differential du is just e to the x dx, and I see that here. So I'm going to bring the e to the x out and put it next to the dx, and that just leaves me an understood 1 up in the numerator. And now it looks like the game is over, because the e to the x dx is exactly du, and I have 1 over u. So when I substitute, I get rid of all my x's, and I've got the integral of 1 over u du, which is the formula just above, and that gives me the natural log of the absolute value of u plus c. And then get rid of the u. Now I will say something here that may not be important at all. I have not even tried this, but if you put this answer in just like this, WebAssign should be fine with it, but the only reason to put absolute value around something is to keep it from being negative. And if you think about it a minute, raising e to a power cannot possibly give you anything negative, and adding 4 to it assures you that you get a positive answer. So actually, in this particular case, you could replace those absolute value symbols with just parentheses, because there's no danger of it being negative. But I'm pretty sure WebAssign will accept that answer with the absolute value, so you don't really have to go through that thought process. Try it and make sure I'm right. But I think that WebAssign's fine with leaving those absolute values in there. It's just that in a problem where the argument of the logarithm can't be negative anyway, then it's redundant to put the absolute value. But like I said, I think WebAssign's fine with the absolute values being there. Go work problems over and over and over again. Write all these basic formulas down in one place so that you'll have one place to look for formulas, because as you're mixing things together, you're going to be using one formula here, one formula there, and you need to have them all together. So create you a summary sheet with all these formulas on it so that you can refer to them when you're doing these problems. And practice, practice, practice. There's nothing wrong with making mistakes and learning from them. In fact, that's really the only way to learn math. You've got to do it that way. And if you're not willing to, I think it's going to be to your detriment in the end. So take the time learning the basics that in the long run will pay huge dividends in the end.